talking about virtual memory. So to the application, the memory is virtual, right? Like, so when you allocate some memory from the application, say you do a malloc, what you get back is a pointer, right? So pointer is nothing but a virtual address. It's actually an integer that is containing the virtual address of the where you want to actually place your data structure, for example. And all these instruction, load, store instruction, they carry virtual address. Okay, that is because that is what the software can see. However, the hardware uses physical address. So, for example, that is the you can actually think of the real address where the data is located. For example, you can think of an address in the DRAM, right? Like where actually the data reside. So when an application executes, which means that a process is running, an application that, when it is running, we will call it a process. Then this, of course, it will do, load stores with virtual addresses, and these virtual addresses need to be translated to physical addresses at runtime. Okay, so this is the crux of what the virtual memory does, and we'll see next how this is actually achieved, what is the purpose of it, and so on. Okay, so think of a particular process that is running, and it is trying to access some address, say 1000 here, right? Let me see. Yeah. At the same time, what can happen in a system that another copy of the same application could run on the same system as well. So that process also try to access the same address 1000. But in a physical memory, you would actually have only one of this address, like 1000. So how do you manage such a situation? So for this, you really need to decouple the application or process's view of memory from the real addresses or physical addresses. And that's what the virtual memory does. So each process can think that they have this particular address 1000, but what you would, and this is called the virtual address, and each of these boxes, all the set of addresses that is available to a given process is called the virtual address space. And at the runtime, this will be actually mapped to a physical address or the real address where the data will actually reside. And that could be, that need not to be in that address 1000. It can be something else. You would just map it to some real address, as long as you can actually given this address 1000 and also given the process that is trying to actually access. Yeah, as long as you can find out where the data actually located, the real address, you are good. And this layer of indirection between software's view of memory and the hardware's view of memory is what we generally called the virtual memory. And here at a very, very high level, so there is two questions, right? One is, who decides what virtual address from a given process? There can be hundreds of processes running on a system at a given point of time. So who decides, a given virtual address of a given process is mapped to what physical address? So that is decided by the operating system, and it manages all these scripts and manages all this mapping, while typically the hardware is responsible for looking up that mapping that the operating system creates and mapping the virtual addresses to physical addresses at the runtime when they are needed, when the load stores are actually happening. As I mentioned that each process has its own view of memory, and that is a virtual memory, virtual addresses. So all the set of addresses that it can actually access is called the virtual address space. For example, in a typical system, you can have a 64-bit system. You might actually have up to say 48 bits of virtual address available, and that will actually let you access, say, between 0 to 256 terabyte of address space. Okay, we'll see some of these, but that's what the virtual address is. It's a contiguous space. And say the real addresses we call the physical address space that primarily consists of the real addresses like those addresses on the DRAM. It would also consist addresses that are mapped to IO devices, but we would not get into that. For now, you can just assume that the real addresses on the DRAM, we'll call it the physical addresses, and all set of such addresses we'll call the physical address space. And another terminology, whenever people refer to this this terminology called memory management unit or MMU, they are in general talking about the part of the hardware that is responsible for translating virtual addresses to physical addresses at runtime. So those are the general terminology that is used in the virtual memory. Now the question is, as you can see, that the virtual memory, what it actually introduces an level of indirection, and any indirection will come with some amount of overhead. That's obvious because you have to go from every load store, you have to go from virtual address to physical address before you can actually complete your cache lookup, for example. Even if it is, that means that you'd, likely to pay some overheads, performance overheads, and so on. So the question is, then still, why have the virtual memory? So there are many fundamental reasons, and virtual memory is one of the reasons, abstraction that has made, that our software world kind of grow, because it actually decouples the view from of the memory from that of the given system or the hardware. So what are these? First of all, you can see that each application can think that they have a really large contiguous region of memory, that is the virtual address space, without worrying about what physical memory, the real memory that are free in a given system at a given time. Think of this. So you write a program, you compile it, okay, and these are all would actually would use the loads and stores. These are all put in as virtual addresses, and this particular software then can run in millions of computers. Each of them can have different amount of physical memory. Not only that, even for a given memory, a given system, they at different points of time, different amounts of real memory or the DRAM would be free. So you don't have to, as a programmer, when you are writing applications or when the program getting compiled, you don't have to worry about that. If you did not have the virtual memory abstraction, you would have actually required to adjust all this memory for each system and for every time you run on that system, because the amount of physical memory, what physical memory is free, would change over time, right? So this is fundamental in which to how we actually write software. So that is one thing. There are the other things is that, as you say, like, what memory is free at any point of time is, something that the application writer does not need to worry about. The responsibility of managing that free physical memory or DRAM is on the operating system. So operating system knows what physical memory is free, and it also, as you mentioned, is responsible for creating the mappings between virtual addresses and physical addresses. So based on what memory is free, it can actually choose, what to map a given virtual address requested by a given process at that point of time when the memory is actually required. And once that mapping is set, the hardware can look up that mapping, right? There are other benefits, for example, isolation between the processes. If because there can be hundreds of processes that are running on a system at a given point of time, you don't want one of the buggy process to create trouble for other 99 processes that might be running on the system at the same time. Since each process have access to its own virtual address space, it cannot actually look into another process's virtual address space. Any memory-related bug that will actually be isolated within that particular process itself. So if it does something wrong, a segmentation fault say happens or something like that, then that particular process that is buggy, application that is buggy, that will die, that will crash. But it would not actually crash the other processes that are actually running on the system. And that's thanks to isolation provided by virtual memory. Then you can have within a virtual address space, you can have different protections, right? For example, you might want to make sure that the code region, because that would be also within the virtual address space of the um, given process, that should not be written to. You can actually put permissions such that they cannot be even mistakenly be written to. Some of the portion of the memory you want it to be read only. Some portion, okay, can be read write. So all this protection of memory can also be or is actually enforced by the virtual memory subsystem. So these are some of the fundamental benefits of why you want to have the virtual memory abstraction, even if it actually costs you some performance, because it is fundamental to how we can write software. So this is our agenda. So we'll actually start. We have already covered what is virtual memory. We'll talk about some of how the virtual memory is actually implemented in the hardware, and we'll also then look into how the software, particularly the operating system, manages virtual memory. So we'll do it quickly. The way how we'll actually look into the hardware side of things is that we'll go from the simpler things like base and bound register to more contemporary like paging. And we'll see each step. We'll see why we needed to evolve from the say base and bound to segmentation, segmentation to paging, and so on. Okay, so base and bound register idea is very simple. We go to this back to our previous picture, and let us assume that this solid green portion of the virtual address space of the process one is currently allocated, which means that the application that process one can use those virtual addresses. If it accesses load stores with those virtual addresses, it should be translated to physical memory so that it can access the data. So what the base and bound does, base just contains the offset into the physical physical address space to which this region of virtual address space, this solid region of virtual address space is mapped, and bound make sure that where that region actually ends. So basically, when you get a virtual address for a given process, you will actually look at the base, which is the offset. You will add that offset and make sure that it is not beyond the bound. Okay. So that's very simple. And each process can have different portion of their virtual address space allocated, and each of them will have their different own base and bound register. Base and bound values. So what really actually happens is that each CPU core can have one set of base and bound register, but remember that there can be hundreds of processes that can be, maybe one running, but there can be hundreds of processes that are live or runnable at any given point of time, and each process will have own values of base and bound registers. Okay. Operating system, as it is responsible for mapping virtual addresses to physical addresses. That's what will assign the base and bound values to each process. And whenever a given process is getting context switched in to run, its these base and bound values are part of its context, and those values are actually put into that corresponding course base and bound register so that the hardware can actually look into it and do the translation at the runtime. So this is not used currently, but very old systems like Cray1 used something like this, one of the early virtual memory systems with the virtual memory, commercial systems with the virtual memory. Of course, it has a lot of disadvantages that are actually obvious. You have one contiguous chunk of memory that you can actually allocate. You need to have free contiguous physical memory to do use this to map a region for a given given process. So this is not really, and also freeing up memory is hard. You can do it only at the edges. So this is not really useful for modern, more complicated software. So next comes the segmentation, where the idea is that instead of one base and bound values, why don't we actually have 5 or 6 of them? That's what the segments are fundamentally. And each process can have its own 5 or 6 base and bound values. So they become multiple segments, right? Typically, segments are associated with semantics of that region of virtual address for what it is getting used. So a part one segment can be there for keeping the code. There can be other segment which is for the stack, which is another segment that is for the data. So this is related to a typical semantics of the memory region that an application would actually use. But fundamentally, these are each of them are nothing but are base and bound registers. So how this really works is that there would be a segment table for each process that will be created by, as mapping is managed by the operating system. It will be managed by the operating system. There will be for each of the segment, like stack segment, code segment, data segment. There will be some protection values, read, write, read, or read, whatever those values are. There will be some base. This is offset. Remember from the previous discussion. And the length is essentially nothing but effectively the bound, right? And how the virtual address will look like is that it will come with a when the load store happening, it will have an virtual addresses broke up like this. You will have a segment selector identifier and an offset within that segment. So what happens for the hardware is that it will actually first look up the using the segment ID, it will look up the segment table, and then it will check the permissions and check that okay, offset is within the length. And once that happens, it adds that with the base, which is the offset, and finds where the physical address corresponding to that virtual address is located, right? So in a say x86 32-bit systems, there used to be there was segments, and it had segments like code segments, stack segment, data segments, and also some other segments like extra segments and ES, FSGS, and so on. And how do you select the segment ID? Some of them are selected by the compiler. Some are like you have the programmer has to select them. So of course, the advantages of the segmentation over the base and bound is clear. You have more number of base and bound effectively. So some of this constraint that okay, there will be one allocated region goes away and so on. So the main problem with the segmentation is that there is what is called the external fragmentation. So let us assume that this is how the at a given point of time there are two processes, and this is the physical memory, and the white portions are the unallocated or free physical memory, right? At this point, there is one more process, the process 3 comes, which wants to allocate a really large portion in its segment. Now, what you can actually see that if you add up all these white spaces, free physical memory on the physical address space, you could easily support the need for mapping this orange processes segment. But unfortunately, none of these white spaces or free physical memory is big enough, or like they are not contiguous enough. This is actually broken up. So what it means is that you cannot run this process 3, although you had in aggregate you had enough physical memory. It's just that they were not contiguous enough. So this is the thing that is called the external fragmentation, that even though you had memory, if in a free memory, you could not allocate it. It got, because the physical free memory was fragmented or non-contiguous. And this problem comes because each segment of size n byte requires n bytes of contiguous free physical memory. And also, like, it's not, the segmentation is not completely transparent to applications. So that's the reason came the paging. Here the idea is very simple. Instead of allowing different segments to be of different sizes, the idea is that allocate, deallocate physical memory, allocate, deallocate any memory in the same size, or this is what called the pages. Okay, and typical page size in say x86 systems. Also, like in say ARM, the default could be 4 kilobyte. Okay, and research page sizes are typically smaller. The reason we'll see shortly, but the big advantage here is that there is no external fragmentation. The reason is, if you think of it, like if in your system you had only one 4 kilobyte of free memory is available, since the applications can request memory only in the chunk of 4 kilobyte, even that 4 kilobyte can be used, right? So you chunk up, you basically make sure that you allocate, deallocate both virtual address and physical address in the granularity of pages, and then each page can be mapped to different physical pages at the granularity of pages, right? And in terms of terminology, this say 4 kilobyte chunks in the virtual address space is called pages, while those 4 kilobyte chunks in the physical address space typically called physical page frames. Okay. Now, of course, the advantage here is that there is no external fragmentation, and it still provides and a view of contiguity of virtual address space. It can still, application can think it is a contiguous memory, but each page can be completely scattered or mapped to different locations in the physical address space, right? So that's the advantage it provides. And all the processors today would actually use paging in some form. Okay. So one of the disadvantages of a paging, and this is one of the reasons that we want this page size not necessarily too large, is because what's called the internal fragmentation. Now the problem here is that if you require say 128 bytes, the minimum you can allocate is 4 kilobyte. So there is a chance that this 4 kilobyte minus 128 byte, that might be wasted, right? You just required 128 bytes. So this is called internal fragmentation. And as you can see, the larger the page size, more is the chance of such wastage. And this will be wasting physical memory once you have allocated a particular page. So that can be costly. That's the reason that you may want to actually keep the page sizes smaller. Otherwise, there will be more and more internal fragmentation. So how, at a conceptual level, the paging works? Now, the virtual address has two parts. One is page offset, and another is virtual page number. So page offset is dependent on the page size. So let us assume the page size is 4 kilobyte, which is typically the standard. So then the least significant 12 bits would constitute the page offset, and the other bits, the most significant, whatever the rest is left, is called the virtual page number. And what you have to actually do, the hardware has to actually do to translate is look up a page table to translate it is virtual page number to physical page frame number. And you can think of, there is a table which is indexed by the virtual page number, And then there is also a protection. It will check the protection, and then you look up the page table. Uh, what is the physical page frame number. And once you have that, you can actually add the page offset or concatenate the page offset to the address. The physical page frame number that you got. You add the page offset, and you get the uh, actual physical address where corresponding to the given virtual address where the load or store is destined for, right? So that's how, conceptually, this is how it actually should work, the virtual address. However, there is a problem here. The problem is the page table would get really big. Since you have to actually keep mapping, a separate mapping for each of the 4 kilobyte page sizes, and each page table entry could be 8 byte long. Say in a typical x86, it's actually 8 byte. So if you do the calculation and assume that the virtual address size is 48-bit long, then if you do the calculation, I think it will come out to be around, the page table itself needs to be around 512 gigabyte. And remember that each process has its own virtual address space, which means that they have to have their separate page table, because each virtual address space will have its own mapping, right? So now you can see that this is really not realistic, because just keeping the page table, just the mapping would be too much of taking too much of memory, and it would not work out. So how do you manage this? Now, toward this, the first observation is that although you can have 48-bit of virtual address space, but these are sparsely allocated. Most of the portion of the virtual address space is typically not used. Because think of it, like, what program you have written that would require 128 terabyte of memory that you have actually allocated. Even if you not touched all of it, it's not like unlikely, right? So what it means is that most of them, it would be sparsely allocated. So how you can actually take advantage of it? And you take advantage of it in a way that can actually reduce the size of page table and should reduce it dramatically. So that's why typically the data structure that is used for page table is not a flat table, but a multi-level tree structure, typically a radix tree structure. So how it actually looks like? So now we'd make it more specific to 64-bit x86 page table. So because that is part of this is part of the ISS specification. By the way, if you have any questions, please feel free to ping me. Ask the question. Unmute yourself and actually ask the question, because I cannot actually see anything coming on the messages. Okay, going back here. So how the page table structures looks like, the typical page table structure looks like it for, say, take an example of x86, which is like, say, Intel or AMD processors, is that it is a 4-level tree structure and with 512 array, means like each node can have up to 512 children. Okay. And this is a radix tree structure indexed by the virtual page number. So the key, the primary way how it actually saves the space is that if there is a portion of the address space that is unallocated, then the subtree that is supposed to actually map that region of virtual address space would not exist. So now you can actually see that this tree will be very sparse, because most of the portions of the address space would not be allocated, and only for the locations that where this virtual address space is allocated, only for the subtree that is needed to map that region would be there. Okay, so we talked about, okay, there is this 48-bit virtual address space. So that is around 256 terabytes. So what you would actually do at the top level is that the top level node will effectively map this entire 256 terabyte, but it will have up to 512 children. Okay. Now there would be so the middle 1 terabyte portion of the virtual address space is unallocated. Then all and each, so then what it means, like each of these these children, they are actually, since you have broken up this 256 terabyte in 512 pieces, each of these pointer to the next level of node is pointing to or representing 512 gigabyte of virtual address space. So if there is in a middle portion that is like, or say 2 terabyte or 4 terabyte long, that is completely allocated, so then all the pointers that are actually going to point to that region would not be present, which means that the entire subtree for that region would not be present in that in a page table. So all those pointers will be null. For the regions which have mapping, that 512 region, 512 gigabyte, say some portion of that 512 gigabyte of the virtual address space is mapped, then for that there will be a next level of node in the page table. Again, that node will be broken up in 512 pieces, which means that each of these would actually point to a 1 gigabyte or represent 1 gigabyte of contiguous virtual address region. Again, within that, some of this 1 gigabyte region would not be mapped, but for which there will be a pointer to the next level of the page table. Again, 512 pieces will be chopped up, which means that each of these each of these pointers, their children would actually point to a 2 megabyte region of virtual address space. And now at the last level, the fourth level or the leaf level of the page table, each of this node would actually represent 2 megabyte mapping for 2 megabyte of contiguous virtual address region, within which there might be so many 4 kilobyte region. There will be actually 512 4 kilobyte region, and some of them would be mapped. And for each of them that is actually mapped, it would contain the physical page frame number. So to find the physical page frame number corresponding to a virtual page number, you have to walk or you have to look up this tree from the root to the leaf, and then only you will find the corresponding physical page frame number. And once you have the physical page frame number, you can use the page offset along with this, add it, and actually you have to concatenate it, and then you would find the physical address corresponding to the virtual address you are actually looking for. We'll look into how this process really works shortly. But remember that each process has its own virtual address space, which means that operating system will maintain one page table per process. And operating system will update this page table and delete entries, which are also called the page table entries or PTEs. And this is a data structure that we talked about here, like 512 array radix tree. This is something that the operating system manipulates, creates for each page table. But this is something that the hardware at the runtime should look up. So it has to be an part of some contract. And this is, that's the reason the page table structure is, codified in the instruction set architecture. So different instruction set architectures like x86 or ARM, they can have slightly different, type of data structure or some different, meaning of the bits that are, assigned for page table entries, and that would be mentioned or specified in the instruction set architecture, because this is part of the hardware software interface. Just for the sake of clarity, both x86 and ARM, both of them uses this radix tree in a structure. I
Sir,
think
I
there
have
is
a
a
doubt.
question. Yes, go ahead.
Sir, like in the previous one, there were like 512 page, I mean, mini pages. So that's like,
Mini
I think there
pages.
will be like,
Mhm. Go ahead. Go ahead. Finish your question.
so that there will be like so many levels to access nodes. So that means like there is going to be so many added latencies, right?
Yeah,
To
we'll
access.
talk about that. Yes, we will talk about that. Yes, it is true. So the trade-off here is that it's not mini pages. It's just that a page table structure, and those are actually pointed to child nodes. This is just a tree structure, right? And you will have, and you can have each node can have up to 512 children. That's the thing. Okay, yes, you're right. The trade-off is that you're trying to actually save memory uh, for the page table, but at the same time, when you are trying to do translation, so then as we talked about, you have to start from the root and go till the leaf before you can get the physical page frame number, which is necessary for translation. Right. So instead of one lookup to a flat page table, you now require a number of accesses equal to the number of labels in the page table, which is here in this case 4, the newest generation of processors from Intel and also upcoming in AMD is this the depth of the page table has become 5. So it can be 5 accesses or 4 accesses, right? So that's too much. We'll see how to actually reduce that shortly. Okay. But before we do that, yeah, the question is that how this page table is actually looked up, right, by the hardware. How do you actually access this page table? Given a virtual page number, you have to you look up this page table to translate it to the physical page frame. Now, the first thing that you need is that where is the root of this page table located? So that information in x86 is kept in some register called CR3 for each core for the given process that is running. So this value of the root of the page table is part of a process's context. So when operating system actually switches a particular process to run, what it will do is that it will take that root of the page table pointer from the processor's context and put that value in the CR3 register of the corresponding core, so that the hardware can find out where this page table is located at runtime. So then what you do, this is where the virtual address it needs to actually translate. So offset, you don't need a translation. We have already talked about it. What you need to translate is the virtual page number. And that you remember this is a 48 bit. So if you take the 12 bits out, it is 36-bit virtual page number. So then you will actually chop this 36 bits in 9 bits in portions. So 4 into 9, 36. What you will do is that take the top 9 bits, use that to figure out which of the 512 entries this correspond to the given virtual address, the virtual page number that you need to do the translation for. So that will select 2 to the power 9, so one of the 512 children. Once you've found that, you look up the pointer and go to the next level, find out which next level of node at the next level node that you should actually look up. Once you find that, you use the next 9 bits to find out which of the 512 entries in the next level you should actually look up. From there, you get a pointer to the third level. As you get pointed to the third level, you use the same trick, the next 9 bits, to figure out which of the 512 children you should look up. That will take you to the leaf level. Once you are in the leaf level, there are 512 possibility. You take the last 9 bit to find out which particular page table entry that would have the corresponding physical page frame number corresponding to the virtual page number that you are looking for. There you go. Once you have the physical page frame number, you concatenate it with the page offset, and given the virtual address, you get the physical address. That's how the page table is looked up. And the question is, who does this lookup? It is the hardware. And the portion of the hardware, the MMU, that actually looks it up is called the page table walker. Okay, and input to this, you can think of it as an actually final state automation. The input to it is the root of the page table CR3 and the virtual page number, and it will actually find out the physical page frame number. And if it doesn't find it, then it creates a page fault. We'll talk about that later. And each CPU core will have its own page table walker, sometimes more than one in the newer processor. Okay. There is other alternative as well, that what you can actually use a software page table walker, but this is not used in the current processor because this is very costly, so we would not get into the details of this. So just in the ARM and x86 processors, the Intels or like ARM processors, they all use hardware page table walkers. So that's what we will actually, and if you want to know more about it, some older machines that like Spark from Sun or Oracle used to have software page table walker. Now the problem that one of you actually mentioned. Now this is the problem with this is that page tables like structures like that. Hey, look, this it can save memory in terms of page table size, but you require multiple accesses to the page table to do the address translation, which is not acceptable, right? It will add a lot of overhead. Like just to do a single memory access before you can complete a cache access, you have to do 4 lookups to the page table to find where in the physical address it is actually located. That's where comes the translation look-ahead buffer or TLB. So what it does, the observation is the same principle of locality. You remember that we talked about there are a few things that last class we talked about, like there are a few philosophies that the hardware designers or even in general systems actually follows. One of them is principle of the locality. Here you often find that the same addresses or the same addresses in the same page is accessed again and again. So why not take advantage of it? And that's where the TLB comes in. The TLB actually contains, given a virtual address, what is the physical, given a virtual page number, what is the physical page frame number, in a kind of a special cache that contains only the virtual to physical address mapping. Okay. And who actually fills it up? It is the page table walker. When you miss in the TLB, you have to do a page table walk or do a translation. At that point, you will find that translation given a virtual page number, what is the physical page frame number. And once you find that, you'll put in the TLB in a hope that that same page number would be accessed again soon. So that's what the TLB does, so that you don't have to do a page table walk on every time you do a load store, because every load store is carrying only the virtual address. You do the page table walk, which is costly, only when there is a TLB miss. So where it is actually, how these TLBs and the page table walkers are located. Typically, each core will have 2 levels of TLB, level 1 and level 2 TLB, just like you will have caches, similar to multiple levels of TLB, multiple levels of caches. You will have level 1 and level 2 TLBs, and then you'll also, each core will have its own page table walkers. Okay, so that's how conceptually where the TLBs and the page table walkers are located. In a typical modern processors, the number, how the typically the TLBs actually TLB hierarchy looks like, or how their sizes are. You would have 32 to 64 entry in L1 TLB and L1 TLB, which can be fully associative, or some 4 to 8 OS associative. You'll have between 1,500 to 2,500 L2 TLB entries. It will typically be 8 to 16 OL set associative, and you'll have 1 to 2. Actually, the latest processor, they have now started having 4 page table walkers in each core. Okay, so each core will have its own set of page table walkers. Okay, so putting it all together, just a minute. I forgot to cancel a meeting with one of my students. I'll just let them know. Okay, sorry for that. I forgot to tell my PhD students. Okay, so how the whole process actually works, putting it all together, is that, as we said, that load stores carry virtual addresses because applications know only virtual addresses. So virtual address is then divided in virtual page number and page offset. This virtual page number is then used to look up the TLB on a hit. Life is good. You don't have to actually do actual address translation through the page table. You just corresponding to on a hit, you actually on a hit to the TLB, basically you get the page frame number, concatenate with the offset, and you get the physical address, and you use that to look up the say caches. On a miss, you have to look up the page table. This is where the page table walker part of the MMU, the hardware, actually comes up. It knows where the given the process, because each process will have its page table, but which process, the given process that is running at that point, that CR3 would be registered. This is a control register 3. CR3 for x86 will actually point to the page table, the root of the page table, and using that, the page table walker will then walk the page table. It knows the data structure because it is part of the ISS specification. If the address mapping is found, it will return it to the TLB. The load store will actually be tried. It would now actually complete the cache access, and so will complete with the physical address that it finds, and the TLB would also be filled up with this, but in this mapping between virtual page number and the physical page frame number. The next time the same page is accessed, you will find it in the TLB. Okay, and if there exists no entry in the page table, that can happen too. We'll see why soon. Then what really happens is that this is when the page fault gets triggered by the hardware. And page fault triggering means that, okay, hardware gives up, say that, okay, the entry that you are actually looking for, given the virtual page number, that doesn't exist. So I give up. I don't know what to do. So at that point, it actually invokes the operating system. Okay, this is done through a facility called general protection fault, which is when the hardware gives up and asks the operating system to take over. So we'll see next how all this, the role that the operating system plays, the software part of it plays to manage this, virtual address space. That will make, make it clear that how the, why this page fault comes and so on. Okay. So far what we have done is that we have also looked into hardware implementation and the role of the hardware in the virtual memory management. Now we'll look into the software management of the virtual memory, or what the role that the software plays. Okay, you have a question?
Sir, I have a question.
Sir,
Am I audible?
You are audible. There is an echo, but yeah, go ahead.
So, sir, I understand that private L1, L2 caches data can be passed across cores. So same way, since TLB is also cache, so is it like what is why it is not done like TLB information? Why is it not passed across cores? Is there any reason for not doing that?
Passed across course. Oh, you mean by share? What is it? Why it is not shared?
Yeah, yes, sir. Like because
Okay.
L1 to cache data is passed like shared across cores.
L3, last level is shared. Okay, think about it. Okay, there is a reason for that. Why don't you actually take this question at the end of this class? Okay, there is a
Okay,
good reason for that, and it's a very good question. Keep thinking about it. Others can think about it as well, and then we'll actually chat about it at the end of the class.
okay, definitely, sir. Thank you.
Sure. Okay. So when you
sir, I
say
have a
software,
doubt.
yeah. Okay, go ahead.
Sir, for that slide, right, where you showed
Mm-hmm.
the page table walk,
Let me go
there
back.
was a node which did not go all the way through the level 4. So in the middle, right, in level 2.
This one.
Yes, sir. For that, how
Okay.
does lookup work?
No. So basically, this is schematic. So So I did not like it did not it is just there to actually show you the basic process. Doesn't necessarily mean that that node would not be there. It could
Okay,
be
sir.
there.
So always it will
Some
take 4 cycles for the page table walk.
not 4 cycles. The memory accesses can take more than 1 cycle. Each of them, it can actually
Okay.
take even more. So that's not the point, but it will take like you can think of it 4 accesses. Okay. Now here is a qualifier that we would not talk about in this class. We cannot actually talk about advanced topics. There is a concept called large pages or huge pages to reduce the overheads of page walks. And there, the page walks can terminate early. For example, if someone uses 1 GB page, then for mapping a portion of a virtual space, it can terminate even in the second level. Unfortunately, this is advanced topic we would not talk about here, but since you asked, I just wanted to qualify it. For now, you can assume that all of the every time a page table is kicked in, it will take at least 4 accesses. But if the page table depth is 5, then just a minute, something happened. Okay, so this is what just happened. There was somebody cutting a tree that fell into our balcony. Anyway, fine, we'll deal with it later. For now, you can actually assume the number of accesses, memory accesses you would require to do an in a page table walk would be equal to the depth of that number of levels of the page table, which in this case we are taking as 4. Latest processor will have it as a 5. Make sense?
Okay, sir. Got it. So one more doubt. When we do the context switching
Quick.
between
Yeah.
processes, right?
Yeah.
The TLB is completely cleared, right?
Yes and no. There is something called ASID, newer processor called address space identifier. So it may not clear it. It will clear it for that given address. So what happens is that. So here is the thing. So at a high level, if you do not have an address space identifier, then you would clear the you would actually clear the TLB, flush it. Okay. However, newer processor, they actually can tag TLB entries with address space identifier, which actually identifies which process it belongs to. So then you do not actually need to do it. The reason is that since each process has its own virtual address space, then if you do not have an address space identifier, you have no way to know which process's virtual page number that a given TLB is mapping to, right? Because the same virtual page number can be mapped from different processes virtual address space, and they should be treated differently because they can map to the different physical addresses. Right now, the newer processor also has this tag by which they can identify at least among few of the processes, so they don't have to actually flush the entire content of the TLB if you have the address space identifier enabled. Okay.
Okay, sir. Thank you.
All right. Let's move on. There is a lot on the software side. Let's do quick. Okay, software management. So this is where we'll actually skip the physical memory allocation a little bit, but we'll talk about what role the operating system actually plays. Remember that when the application does memory allocation, like in malloc and anything, right? It is nothing but it is allocating virtual addresses. Okay, it is not really allocating physical addresses. Okay, the real addresses. And operating system is responsible for keeping note of actually managing the virtual address space for each process, and also managing the physical address space. Now, how this virtual address space are actually looked like? This is a Linux example. This is a convention, nothing really fancy about it. But typically, you would actually keep the code, the static data, and say heap portion in the lower part of the virtual address space. Okay. and the stack would be at the top of the virtual address space. That is where it will be allocated, and it will grow downward. And in the middle will be dynamically allocated memory regions for that particular application or the process. And the heap grows upward. In the middle also, all the files that are actually mapped, the libraries that are actually used by the application, that will all go in the middle of the virtual address space. And this is a convention that is used in Linux. This is nothing like something that you require, but this is how typically it looks like. Now, operating system itself is nothing but a software. It's a multi-threaded software. So think of it, it has to actually manage these virtual addresses regions, which means that it needs data structures, different data structures to keep track of what portion of the virtual address space of each process is allocated and so on. So how this data structures looks like, and this is an example from Linux, and it needs to be a little bit specific, otherwise you would not get the taste of it. Remember, you might have actually read about the process control block, or PCB. So in Linux, this is effectively represented by a structure. It's written in C, task struct. It will have a lot of information like PID, the status of the process running or waiting and so on, number of open files and a list of signals and many other things. It will also have a pointer to the virtual address space that is managed by another data structure called struct. So for each virtual address space that are currently there, which means that each process that are currently there in the system, live in the system, Linux will have one instance of this data structure called struct, one object of this data structure. Okay, and that will have information like pointer to the page table root. This is the address that is actually put on the CR3 when this particular process gets running, but you have to keep all this information somewhere, right? This is the part of the process context, which will be in the memory, and this is kept in these data structures. So it will have things like, okay, what is the starting virtual address and end virtual address for the stack and so on. But the more interesting part that we want to focus on is this, what's called the VMA area pointer. So this is actually point to a linked list, and each node of the linked list would point to would have push. It actually represent a contiguous region of virtual address space that is currently allocated. So remember that portion of the for each process there is a virtual address space, and a portion of it is only portions of it is allocated. And this contiguous region of allocated virtual address spaces, they will be represented by a node in this linked list, and these nodes are called VMA. It has a starting virtual address, ending virtual address, and also the some kind of a flags and protection information that is that is allowed, and that actually characterizes that region of contiguous virtual address that is actually allocated. Okay, so remember, only the allocated virtual address regions are tracked because of the the previous reason that most of the virtual address regions of a virtual address space will be unallocated. So how do you allocate? How do you actually request new virtual address regions to be allocated to operating system? There is a system call called mmap system call. We would not go into the details of its parameters and so on. We don't have time for that. But this is where you can actually application can invoke a mmap system call, tell what is the size of the virtual address region that it wants to actually allocate, and operating system will go and mark that allocated. One constraint is that the size of the allocation request has to be a multiple of 4 kilobyte. It cannot be below 4 kilobyte. Okay, and it can be multiples of 4 kilobyte. So once the Linux gets this mmap system call, what it does is this goes and actually updates this linked list and notes down that another region of virtual address space within that particular process that actually invoked that mmap system call in that process's virtual address space. So it will go to that in a start struct for that, go to their struct, find out this BMA area, and then it can actually extend one of the existing virtual address region, or it can add one more node based on whether it can keep it contiguous or not. If it want to keep it contiguous, then the protection information of flag needs to be same, and some constants are there. But in general, the meta point here is that once operating system gets such a call, it just goes and updates its internal data structures, pointing out, remembering that, okay, this another region of the virtual address space for the given process is now allocated. Now, yes, the another system call that is actually used specifically for extending heap memory is called SBRK or SBREAK. This is similar in spirit, but it only extends this special this special memory region, which is the heap memory region, which grows upward, and it always have read-write permissions. And the same thing actually happens. There would be virtual, this node in this linked list, another BMA node that will be representing the heap memory region, and that based on whether you are allocating or deallocating the using the SBRK. If you put a negative number, it will actually deallocate. It will change the end BA value for that given for that given BMA region or the given node in the linked list corresponding to the heap. So that's what it all does. So so what you have actually seen so far is that when you are from the application's point of view, when you are allocating memory, you are really what operating system is doing is it is just allocating virtual address region, nothing more. No real memory is allocated. And this is why the demand paging comes in. Yeah. So remember one thing, that when you say application allocating memory, it is not allocating real memory. It is always allocating a portion of virtual address space. That's it. Now, why you do this, why you don't actually allocate the physical memory immediately, is from the observation that often applications allocate a lot of memory, quote unquote, which is like, which becomes virtual addresses, but they do not necessarily use them. Okay. Now, then that will be wastage of physical memory. Physical memory is, which means the DRAM size is constant. You have like a few gigabytes to a few hundred gigabytes, or in the server at most like a few terabytes. On the other hand, virtual address space is abundant. Each process can have up till 120, 256 terabyte, right? So you can waste a few of virtual addresses because they are virtual, right? Not a real. So that's the reason you just allocate virtual addresses when application asks for memory. Okay. So, but then the problem becomes like, if it actually, when it, after allocating, when it really, the process really accesses that memory, that virtual address, you need to, at that point, you do need the real memory, right? And how do you actually find it out? How, that particular address is getting access for the first time. This is why the page fault comes into the picture. Okay. So, and then this is why this is the concept of dependent paging, is that you lazily allocate physical memory only when it is needed. And that's what called the demand paging, and page fault is a key enabler for that. So we talked about this. What would actually really happen? So let us assume that an application allocated a virtual address region, all is good. But what the operating system has done is that it just marked a portion of the virtual address space in its internal data structure, those nodes, that, okay, that portion of the virtual address space is allocated, but it didn't do anything with the page table. It didn't try to actually allocate physical memory at all. So what would actually happen now? Next, the application goes and accesses that virtual address because it thinks that it has allocated that region. Node is, so it will access it through load stores. So load store will carry that virtual address. At that point, the page table walker, at that point, it will actually first look up the TLB. But since it is accessing that virtual page for the first time, it will miss in the TLB. The page table walker will get kicked in. Page table walker will actually look up the page table, but it will not find the mapping for that virtual page number in the page table because it was never allocated, and only operating system can manipulate the page table, allocate, deallocate page tables. So what would happen at that point of time? There will be a page fault triggered, and this is the page fault, and hardware actually gives up to the operating system, say that, okay, you manage it. Now, operating system at that point of time sees that, okay, this is the virtual page number that caused this fault. And then what it would actually do is that it will look up that in that data structure, there's those nodes, BMA nodes, and see if this is a genuine virtual address that the application is allowed to access or not. If it is not, for example, if you are trying to access an address which you have not allocated or you have already deallocated, then what would happen is that you will get a segmentation fault from the operating system at that point of time, and that application will die. If not, it is now finds out, okay, I have to allocate the physical memory. So as a part of handling the page fault handler, then it will find a free physical page frame number. It will grab that, update the page table, and then return from the page fault. Once it's returned from the page fault, hardware will retry that load store again. Now what would happen? It will again look up the TLB. Again, it will miss in the TLB. Page table walker will kick in again, but this time the page table has been updated for this virtual page number with the corresponding physical page frame number. So it will have a page, page table walk will succeed. It will put in the TLB, and the and the access will actually succeed. So that's how the whole demand paging actually works. So this is the something that we already talked about, how the page fault is serviced. We already talked about, like, so it has to, as a part of page fault handling, it make sure that application is not trying to access virtual address region that it is not supposed to or doesn't have the right permission for. And that's the reason that when you allocate memory, you note it down in this operating system's internal data structures, these nodes in the linked list, the BMA nodes, what part of the virtual address is allocated and what part is not. Okay? And if all goes well, then you would find a free physical memory that is available, and operating system knows it. How it manages free physical memory, that's another lecture we would not discuss here. But it somehow here we'll assume that somehow it will actually find a free physical page frame. Once it finds that, it will actually put the page table entry, update the page table, and then return. And the rest, the hardware will take care, because by convention, it will retry the same instruction, and this time it will not fault. Now you might be wondering, like, I allocate not using mmap. I actually allocate memory, my applications using malloc. So why this actually fits in? So by the way, first thing first, malloc is not a part of operating system. It's just a function call. Okay, and malloc, just like mmap, allocates an virtual address region. But what it actually does is this. The problem with mmap is that it is, you have to allocate only in the 4 kilobyte granularity or a multiple of that, right? But often you will have this small allocation, 128 byte, 256 bytes. And if you have to go for always get a 4 kilobyte change, this will waste a lot of memory, right? So what malloc does is that in its backend, it actually talks to the operating system using those system calls like mmap and sbrk. But what it does is that, say you try to allocate 128 bytes, malloc 128 bytes, and the malloc library can go and do a mmap, get a 4 kilobyte portion of virtual address space. Out of that, it will return you 128 byte. Next time you ask for, say, 256 bytes, it would not go and get another system call and get another 4 kilobyte. Instead, it will see that, oh, within this 4 kilobyte page that I already got from operating system, there is space left. So it will return a 256 byte chunk out of the 4 kilobyte say page that it has already allocated. So this is the purpose of malloc. So malloc is basically also maintains a free list, but this free list is for the virtual address regions that are already allocated from the operating system. Okay, and for any large malloc, say if you are asking for more than say 32 kilobyte and so on, it will automatically become a malloc. Only is there to manage small allocation request. Everything else, it's like, and in the backend, it is using the same operating system's system calls like mmap and SBRK. And the goal of it is to reduce the number of system calls. It also wants to actually reduce the amount of memory bloat. Memory bloat is where it's kind of the internal fragmentation that you don't want to allocate too much of memory. And you want to actually reduce the number of system calls to the operating system because those are slow. That's where the switch between hardware user mode to supervisor mode or OS mode actually happens. And there are many malloc libraries. It's not one that is, there is something called, most commonly used is glibc malloc that comes automatically. Google has something called tc malloc that scales really well to large number of threads. There are things like dl malloc, and malloc is a weak symbol. So which means that you can write your own malloc library or malloc function that will actually get executed instead of whatever the say glibc malloc if you write yourself one by yourself. Okay, so putting it again all together, so how this whole thing actually happens is that in application first allocates memory. It can be malloc, but ultimately the virtual addresses needs to be come from the operating system. That's the and you use applications actually. Operating system will actually update the VMA regions, those nodes, and so on to find to demarcate a region of a virtual address space of that given process as allocated virtual address range. Later application would use load stores to to access a particular address in the VA range. And if there is a initially it will be a TLB miss, there will be page table walker, there will be like page fault that will be generated to the operating system the first time it actually accesses a given virtual address. And the virtual at that point of time, page fault handler will first see that if it is a legal virtual address. If it is, then it will find a free physical page frame and map it to map the virtual address that you are trying to virtual page number that you are trying to actually access and using the by updating the page table, it will then return from there. And the hardware will retry the same load store. This time it will actually find the mapping, and so that will actually end. This is how the whole process of virtual memory would work. So I think I'll actually stop here. There are a few other topics that I could have covered, but I think this is the basics of virtual memory. So it might be actually good to if you have some questions. We already have one. But if we have other questions, this is the time for you to actually ask. Okay. Before we go into other questions, there was this one question: why we did not, like caches, we did not have a shared last level TLB. Now, it's not that it has not been actually proposed in the research articles, but it is not. This is not what is actually done on the hardware because there is not much benefit of it. The reason is this. Think of this. What the caches are containing, particularly say last level caches and so on, that is physical, based off physical addresses. And there is only one physical address in the system. So if there is some kind of sharing and so on, different processes can be running in different ports and they can make use of the caches. But TLB is accessed and mapped through virtual addresses, and for each process there is a different virtual addresses, and the expectation is generally that different core would be running different processes, which means even in a multi-core, which means that there is no benefit of sharing, because if you have a shared last level TLB, that doesn't make sense, because different so unless you actually share an entry, you would not be able to actually share an entry. Each process will have their own virtual address space. So since this is a private to each process, and your in general system is expecting each core would be running different processes, their TLB hierarchy as well as a page table walkers, these are private. Now you can still argue there might be some benefit if you have a shared last level TLB. Some can actually use some extra capacity left by others and so on. But this will add to the overhead, because you now have to access another level, which is a shared level, which means that it will take longer time and so on. But the benefits will be limited, because you cannot actually share across address spaces, share across this same structure, same entries across address spaces. So you do not have shared last level TLB in the system. Does that make sense?
Sir, I have a doubt.
Yes, sir.
Okay, so what is the
Based
doubt?
on that.
Yeah.
Sir,
Yeah.
so like suppose we had shared TLB, then won't it be like easier to increase the number of threads? Like we can like achieve similar to superscalar without even having
What?
multiple.
So what is that? I don't understand. So,
Sir,
say it
like if
again.
since like I'm trying to think of why we can't have execute multiple cores for single process. So won't that
Multiple
be,
codes.
yeah, why can't we use multiple cores for the same process?
I don't fully understand. I don't think this question is fully formed. So in a process, if it's a single threaded process, there is a single stream of instruction, sequential stream of instruction that is coming. So I don't completely understand for a single process how we use multiple cores, but
Yes, sir.
unless you
That's
don't
what I
actually
think.
have multiple threads. If you
Yes, sir.
create multiple threads, then they share the same address space, virtual address space, because they are part of the same, same
Process.
process. Yeah. So then that can be used in different codes can actually use it, or like if it is, we'll probably talk about later. If there are multiple hardware threads, they can make use of for a single core as well. Those can be scheduled as well. In those cases, I'm actually speculating. This is what you are getting. And then you can actually say that, okay, if there are multiple codes, they are actually running threads of the same process, then they are actually sharing the same virtual address space. Maybe at that point of time, a shared level of TLB makes sense. Yes, that would actually make sense, but that's not necessarily the common case. So that's the reason that current processors actually do not have shared last level TLB.
Yes, sir. Okay, sir. Understood, sir.
Any other question?
So won't demand paging be very time expensive? Like if we have something which can handle virtual memory on hardware, wouldn't that be something better? Because here we have to hand it all over to the operating system and let that take control of it.
Yeah, it's a trade-off between performance and flexibility. Keeping it on the operating system allows you to flexibility, because you can always change the software. Hardware, anything you put on the hardware, it becomes stuck in the hardware, which is hard to actually update and so on. And page faults are relatively infrequent compared to the running length of the application, because you are generating the page fault first time you access a page, but you will access that page millions of times probably. Like only the first time you will pay the cost of a page fault, which like these are called minor page fault. It will cause you 2 to 3 microseconds to handle. So if you make it the page fault onto the hardware, it may not bring much performance benefit. At the same time, on the other hand, it would actually make things much less flexible. That's the reason that you rely on operating system to handle the page fault.
Okay, sir. Thank you.
Okay. Next question.
Sir, I have a question regarding page walker.
Right?
Does page walker access caches L2 LLC caches?
Good question. Yes, it does. So
Okay,
page
not L1,
tables,
right, sir?
no, it does L1 too.
Oh, okay.
Yeah, it does all of that. So basic thing is that in typically in current process it does it previously did not, but now it does access L1 caches too. So as I said, like think of operating system just like another software with some special power, but it's actually at the end of the day as a multi-threaded software. Okay. And it has these data structures. One of these data structures is page table, right? So just like any other applications, when it is accessing the others, our data structure, it will be cached in the data caches. Just like that, page table is nothing but a normal data structure. It will be cached. Its content will be cached in the data caches. Okay. So I need to now go. We'll handle the rest of the questions that you'll actually have in the doubt clearing session. Okay. Thank you.
Thank you, sir.
Thank you, sir.